Hello and welcome. In this video, we will explore Maclaurin series, a powerful tool in higher-level mathematics. By the end of this session, you will be able to define and derive Maclaurin series, understand their convergence, and apply them to solve complex problems. Let's begin with a fundamental idea from calculus, approximating a curve with a straight line. We know that the tangent line at a point x equals a is the best linear approximation of a function f of x near that point. The equation of this tangent line is y equals f of a plus f prime of a times the quantity x minus a. This is a first-degree polynomial that matches the function's value and its first derivative at x equals a. But what if we want a better approximation? A straight line can't capture the curvature of a function. To do that, we need a polynomial of a higher degree. This leads us to the idea of a Taylor series, which is an infinite polynomial that can represent a function perfectly within a certain interval. The general form of a Taylor series for a function f of x centered at x equals a is the sum from k equals 0 to infinity of the kth derivative of f at a divided by k factorial, all multiplied by x minus a to the power of k. In this course, we will focus on a special case of the Taylor series. When the series is centered at x equals 0, it is called a Maclaurin series. This simplifies the formula significantly. The Maclaurin series for f of x is the sum from k equals 0 to infinity of the kth derivative of f at 0, 0, divided by k factorial, times x to the power of k. Let's expand this to see the first few terms. The series starts with f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared, and so on. Each term is determined by a derivative of the function at x equals 0. This formula is the foundation of our study. It allows us to represent a function as an infinite polynomial, which can be much easier to work with for tasks like differentiation, integration, and approximation. Now, let's put this formula into practice. Our objective in this scene is to derive the Maclaurin series for a function. We will work through an example to see how to find the Maclaurin series for a given function. Let's find the Maclaurin series for the function f of x equals 1 over the quantity 2 plus x. To do this, we need to find the function's value and its derivatives at x equals 0. It's often helpful to write the function in a form that's easier to differentiate. We can rewrite f of x as 2 plus x to the power of negative 1. Now, let's find the first few derivatives. The first derivative, f prime of x, is negative 1 times 2 plus x to the power of negative 2. The second derivative, f double prime of x, is negative 1 times negative 2, which is 2 times 2 plus x to the power of negative 3. The third derivative, f triple prime of x, is 2 times negative 3, which is negative 6, times 2 plus x to the power of negative 4. We can see a pattern emerging. Let's try to find a general formula for the kth derivative. The kth derivative, f superscript k of x, is negative 1 to the power of k, times k factorial, times 2 plus x to the power of negative k plus 1. Now we need to evaluate these at x equals 0. F of 0 is 1 over 2. F prime of 0 is negative 1 over 4. F double prime of 0 is 2 over 8, which simplifies to 1 over 4. Triple prime of 0 is negative 6 over 16, which simplifies to negative 3 over a. Using our general formula, f superscript k of 0 is negative 1 to the power of k times k factorial, divided by 2 to the power of k plus 1. This gives us a compact expression for all the coefficients. Now we can substitute these into the Maclaurin series formula. The Maclaurin series for f of x is the sum from k equals 0 to infinity of our expression for f superscript k of 0 divided by k factorial times x to the k. Notice that the k factorial terms cancel out. This leaves us with the final Maclaurin series. The sum from k equals 0 to infinity of negative 1 to the k, divided by 2 to the k plus 1 times x to the k. Let's write out the first few terms to see what it looks like. For k equals 0, we get 1 over 2. For k equals 1, we get negative 1 over 4 times x. For k equals 2, we get 1 over 8 times x squared, and so on. This is the infinite polynomial representation of our function. We have now successfully derived the Maclaurin series for f of x equals 1 over 2 plus x. This process of finding derivatives and evaluating them at zero is the standard method for deriving these series. In this scene, our objective is to understand the concept of a Maclaurin polynomial and how it approximates a function. We will see that by taking a finite number of terms from the infinite Maclaurin series, we can create a polynomial that approximates the original function. The full Maclaurin series is an infinite sum. In practice, we often use a finite number of terms to create a polynomial approximation. This finite sum is called the nth degree Maclaurin polynomial, denoted m sub n of x. It's simply the Maclaurin series truncated after the term with x to the power of n. Let's continue with our previous example. F of x equals 1 over 2 plus x. We found its Maclaurin series to be the sum from k equals 0 to infinity of negative 1 to the k over 2 to the k plus 1 times x to the k. Let's find the fourth degree Maclaurin polynomial m sub 4 of x. This means we take the first 5 terms of the series from k equals 0 to k equals 4. Expanding this, we get 1 over 2 minus 1 over 4x plus 1 over 8x squared minus 1 over 16 cubed plus 1 over 32 to the fourth. This polynomial is an approximation of the function f of x. Let's see how good the approximation is at a specific point, say x equals 1. First, let's find the exact value of the function at x equals 1. F of 1 is 1 over 2 plus 1, which is 1 over 3. Now let's evaluate our polynomial approximation at x equals 1. M sub 4 of 1 is 1 over 2 minus 1 over 4 plus 1 over 8 minus 1 over 16 plus 1 over 32. To add these fractions, we find a common denominator, which is 32. This gives us 16 minus 8 plus 4 minus 2 plus 1 all over 32, which equals 11 over 32. So our approximation is 11 over 32. How does this compare to the exact value of 1 over 3? 11 over 32 is approximately 0.34375, while 1 over 3 is approximately 0.333. The approximation is quite close. This demonstrates that Maclaurin polynomials can provide good approximations of functions. The accuracy generally improves as we include more terms in the polynomial, especially for values of x close to 0. In this scene, we will explore the Maclaurin series for the exponential function, e to the power of x. Our objective is to derive this series and understand its properties. The exponential function is one of the most important functions in mathematics, and its Maclaurin series is fundamental. Let's consider the function f of x equals e to the x. To find its Maclaurin series, we need its derivatives at x equals 0. The first derivative of e to the x is e to the x. The second derivative is also e to the x, and this pattern continues indefinitely. The nth derivative of e to the x is always e to the x. Now let's evaluate these derivatives at x equals 0. F of 0 is e to the 0, which is 1. F prime of 0 is also 1, and in fact the nth derivative of f at 0 is 1 for all n. Now we can substitute these values into the Maclaurin series formula. The Maclaurin series for e to the x is the sum from k equals 0 to infinity of 1 over k factorial times x to the k. Let's write out the first few terms. For k equals 0, we get 1. For k equals 1, we get x. For k equals 2, we get x squared over 2 factorial. For k equals 3, we get x cubed over 3 factorial, and so on. This is the famous Maclaurin series for e to the x. This series has a remarkable property. It converges for all real values of x. This means that for any x, the infinite sum equals e to the x. The interval of convergence is all real numbers, which we write as x is an element of R. Let's look at the Maclaurin polynomial approximations for e to the x. M sub 1 of x is 1 plus x. M sub 2 of x is 1 plus x squared over 2. M sub 3 of x is 1 plus x squared over 2 plus x cubed over 6. As we add more terms, the polynomial gets closer and closer to the curve of e to the x. This scene has shown us how to derive the Maclaurin series for e to the x and has highlighted its universal convergence, making it an incredibly useful tool for approximation and analysis. In this scene, we will derive the Maclaurin series for the trigonometric functions sine x and cosine x. Our objective is to find these series and observe their unique patterns. These series are essential for approximating trigonometric values and for understanding their relationship with other functions. Let's start with f of x equals sine x. We need to find its derivatives and evaluate them at x equals 0. The derivatives follow a cycle: sine, cosine, negative cosine, and back to sine. Now let's evaluate these at x equals 0. F of 0 is sine of 0, which is 0. F prime of 0 is cosine of 0, which is 1. F double prime of 0 is 0. F triple prime of 0 is negative 1. The pattern of coefficients is 0, 1, 0, 1, 0, 1, and so on. Substituting these into the Maclaurin series formula, we see that all the even-powered terms will be 0. The series for sine x only contains odd powers of x. It is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. In sigma notation, this is the sum from k equals 0 to infinity of negative 1 to the k over the quantity 2k plus 1 factorial times x to the power of 2k plus 1. Now let's do the same for f of x equals cosine x. The derivatives also follow a cycle: cosine, negative cosine, sine, and back to cosine. Evaluating at x equals 0. F of 0 is 1. F prime of 0 is 0. F double prime of 0 is negative 1. F triple prime of 0 is 0. The pattern of coefficients is 1, 0, 1, 0, 1, and so on. This time, all the odd-powered terms will be 0. The series for cosine x only contains even powers of x. It is 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on. In sigma notation, this is the sum from k equals 0 to infinity of negative 1 to the k over the quantity 2k factorial times x to the power of 2k. Both the sine and cosine series, like the exponential series, converge for all real values of x. This means their interval of convergence is x is an element of R. We have now derived the Maclaurin series for sine x and cosine x, noting their alternating signs and the presence of only odd or even powers of x. These are two more fundamental series that you should be familiar with. In this scene, we will discuss the crucial concept of convergence. Our objective is to understand what it means for a Maclaurin series to converge and how to determine its interval of convergence. A Maclaurin series is an infinite sum. For it to be a valid representation of a function, that infinite sum must approach a finite value. This is the idea of convergence. The infinite Maclaurin series for a function f of x converges for a value of x if the limit of the nth degree polynomial m sub n of x, as n approaches infinity, is equal to the function's value if f of x. In other words, as we add more and more terms to the polynomial, it must get closer and closer to the actual function value. The set of all x values for which the series converges is called the interval of convergence. This interval always includes x equals 0, because at x equals 0, the polynomial m sub n of 0 is always equal to f of 0, regardless of n. Let's look at some examples we've already seen. The Maclaurin series for e to the x, sin x, and cosine x all converge for all real numbers. Their interval of convergence is x is an element of R. However, not all series converge everywhere. Let's consider the series for 1 over 1 minus x. This is a geometric series: 1 plus x squared plus x cubed, and so on. We know from our study of geometric series that this only converges when the absolute value of the common ratio, x, is less than 1. So, the interval of convergence for this series is the open interval from negative 1 to 1. What happens if we try to use this series outside its interval of convergence? For example, let's try x equals 2. The series becomes 1 plus 2 plus 4 plus 8, and so on. This sum clearly goes to infinity. It diverges. The series does not represent the function 1 over 1 minus x at x equals 2. This highlights a critical point. A Maclaurin series is only equal to the function it represents within its interval of convergence. Outside this interval, the series is meaningless as an approximation. In this scene, we have defined convergence and the interval of convergence, and we've seen that not all Maclaurin series converge for all x. Understanding this limitation is key to using these series correctly. In this scene, we will learn a powerful technique for finding new Maclaurin series from known ones. Our objective is to use substitution to find the series for composite functions. This method is often much faster and less prone to error than calculating derivatives directly. The principle is simple. If we have the Maclaurin series for a function f of x, we can find the series for f of g of x by substituting the expression for g of x into the series for f of x. Let's see this in action. We know the Maclaurin series for e to the x is 1 plus x squared over 2 factorial and so on. Now let's find the Maclaurin series for e to the power of 2x. Here, our inner function g of x is 2x. We simply replace every x in the series for e to the x with 2x. This gives us 1 plus 2x, plus the quantity 2x squared over 2 factorial, plus the quantity 2x cubed over 3 factorial, and so on. Now we simplify the terms. This simplifies to 1 plus 2x, plus 4x squared over 2, plus 8x cubed over 6, and so on. This is the Maclaurin series for e to the 2x. Let's try another example. Find the Maclaurin series for cosine of x squared. We start with the known series for cosine x, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. This time, our inner function is x squared. We substitute x squared for every x in the cosine series. This gives us 1 minus the quantity x squared over 2 factorial, plus the quantity x squared to the 4th over 4 factorial, and so on. Simplifying the powers, we get 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial, and so on. This is the Maclaurin series for cosine of x squared. The series is 1 minus x to the 4th over 2 plus x to the 8th over 4, and so on. A crucial note about convergence. The new series will only converge if the substitution respects the interval of convergence of the original series. For example, the series for 1 over 1 minus x converges for at x 1. If we substitute x squared for x, the new series for 1 over 1 minus x squared will converge for x squared 1, which is also 1. We have now seen how to use substitution to find Maclaurin series for composite functions, a powerful and efficient technique. In this scene, we will explore how to combine Maclaurin series using addition and subtraction. Our objective is to find the series for a sum or difference of functions by adding or subtracting their individual series. This method is straightforward. We simply add or subtract the corresponding terms of the series. Let's find the Maclaurin series for the function f of x equals sine x plus cosine x. We will use the known series for sine x and cosine x. The series for sine x is x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, and so on. The series for cosine x is 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, and so on. To find the series for their sum, we add these two series term by term, grouping by powers of x. We write out the terms and combine them. The constant term is 1. The x term is x. The x squared term is negative x squared over 2 factorial. The x cubed term is negative x cubed over 3 factorial, and so on. Rearranging in ascending powers of x, we get the Maclaurin series for sine x plus cosine x, 1 plus x minus x, squared over 2 factorial, minus x cubed over 3 factorial, plus x to the 4th over 4 factorial, and so on. Let's try a subtraction example. Find the Maclaurin series for the hyperbolic sine function, sinh x. The hyperbolic sine function is defined as e to the x minus e to the negative x, all divided by 2. We already know the series for e to the x. To find the series for e to the negative x, we substitute negative x for x in the e to the x series. This makes the signs alternate. Now we subtract the series for e to the negative x from the series for e to the x. When we subtract, the even-powered terms cancel out, and the odd-powered terms double. For example, x minus negative x is 2x. X cubed over 3 factorial minus negative x cubed over 3 factorial is 2 times x cubed over 3 factorial. Finally, we divide the entire result by 2. This gives us the Maclaurin series for sin x, x plus x cubed over 3 factorial, plus x to the 5th over 5 factorial, and so on. Notice that this series looks very similar to the series for sine x, but all the signs are positive. The interval of convergence for a sum or difference of series is the intersection of their individual intervals of convergence. Since e to the x and e to the negative x both converge for all x, their sum and difference also converge for all x. We have now seen how to add and subtract Maclaurin series to find new ones, a technique that is both intuitive and efficient. In this scene, we will explore another powerful property of Maclaurin series. They can be differentiated and integrated term by term. Our objective is to see how this allows us to derive new series from existing ones. This is a significant advantage of polynomial representations, as it simplifies operations that might be complex for the original function. Let's start with differentiation. We know the Maclaurin series for sine x. The series is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. We also know that the derivative of sine x is cosine x. Let's see if we can get the series for cosine x by differentiating the series for sine x term by term. We differentiate each term individually. The derivative of x is 1. The derivative of negative x cubed over 3 factorial is negative 3x squared over 3 factorial. The derivative of x to the 5th over 5 factorial is 5x to the 4th over 5 factorial, and so on. Now let's simplify the factorials. Remember that n factorial is n times n minus 1 factorial. 3 factorial is 3 times 2 factorial, so the 3 cancels. 5 factorial is 5 times 4 factorial, so the 5 cancels. This simplifies to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And what do you know? This is exactly the Maclaurin series for cosine x. It works perfectly. Now let's try integration. We know the Maclaurin series for 1 over 1 plus x. This is the alternating geometric series. 1 minus x plus x squared minus x cubed, and so on. Its interval of convergence is the open interval from -1 to 1. We also know that the integral of 1 over 1 plus x is the natural logarithm of the absolute value of 1 plus x. Let's integrate the series term by term. We integrate each term. The integral of 1 is x. The integral of negative x is negative x squared over 2. The integral of x squared is x cubed over 3, and so on. We also need to add a constant of integration, c. To find c, we can use the fact that the series must equal the function at x equals 0. At x equals 0, the function is ln of 1, which is 0. The series becomes 0 plus c. Therefore, c must be 0. This gives us the Maclaurin series for ln of 1 plus x, x minus x squared over 2 plus x cubed over 3, minus x to the 4th over 4, and so on. The interval of convergence for the integrated series is the same as the original, x1, but we must check the endpoints. It turns out this series also converges at x equals 1, so the full interval is -1 less than x less than or equal to 1. We have now demonstrated that Maclaurin series can be differentiated and integrated term by term, a powerful technique for deriving new series and solving problems. In this scene, we will learn how to multiply Maclaurin series. Our objective is to find the first few terms of the series for a product of two functions by multiplying their individual series. While finding the full infinite series for a product is generally not feasible, we can easily find the first few terms, which is often all that's needed for approximation. The process is similar to multiplying two polynomials. We multiply each term of one series by each term of the other and then collect like terms. Let's find the first four non-zero terms of the Maclaurin series for e to the x times sine x. First, we write out the first few terms of each series. For e to the x, we'll use terms up to x cubed. For sine x, we'll use terms up to x cubed as well. Now we multiply these two polynomials. We set up the multiplication. We'll multiply the first polynomial by each term of the second polynomial. First, multiply by x. This gives us x plus x squared plus x cubed over 2 plus x to the 4th over 6 and so on. Next, multiply by negative x cubed over 6. This gives us negative x cubed over 6 minus x to the 4th over 6 and so on. We only need to go up to x to the 4th, as higher powers will not contribute to our first four non-zero terms. Now we add these two results together and collect like terms. The x term is just x. The x squared term is just x squared. For the x cubed term, we have 1 over 2 minus 1 over 6, which is 3 over 6 minus 1 over 6, or 2 over 6, which simplifies to 1 over 3. For the x to the fourth term, we have 1 over 6 minus 1 over 6, which is 0. Since the x to the fourth term is 0, we need to find the next non-zero term. We would need to include the x to the fifth term from the sine A series and the x to the fourth term from the e to the x series to find the x to the fifth term of the product. The first four non-zero terms are x squared, x cubed over 3, and x to the fifth over 30. The interval of convergence for the product of two series is the intersection of their individual intervals of convergence. Since e to the x and sine x both converge for all x, their product also converges for all x. We have now seen how to multiply Maclaurin series to find the first few terms of a product, a useful technique for approximation. In this final scene on operations, we will learn how to divide Maclaurin series. Our objective is to find the first few terms of the series for a quotient of two functions. This method is a bit more involved than multiplication, but it's a standard technique for finding series for functions like tangent x. The method is called the method of undetermined coefficients. We assume the quotient is a new Maclaurin series with unknown coefficients. Let's find the first three non-zero terms of the Maclaurin series for tangent x, which is sine x divided by cosine x. First, we write out the first few terms of the series for sin x and cosine x. We'll use terms up to x to the fifth for both. Now, we assume that the series for tangent x has the form a sub 0 plus a sub 1x plus a sub 2x squared, and so on. So, we have the equation. Sin x equals the series for tangent x times the series for cosine x. Now, we multiply the two series on the right side, just like we did in the previous scene. Multiplying the terms and collecting by powers of x, we get a sub 0 plus a sub 1x, plus the quantity a sub 2 minus a sub 0 over 2 times x squared, plus the quantity a sub 3 minus a sub 1 over 2 times x cubed, and so on. Now we equate the coefficients of this new series with the coefficients of the series for sine x. The series for sine x is x minus x cubed over 6 plus x to the fifth over 120. Let's compare the coefficients. The constant term on the left is 0, so a sub 0 must be 0. The coefficient of x is 1, so a sub 1 is 1. The coefficient of x squared is 0, so a sub 2 minus a sub 0 over 2 is 0. Since a sub 0 is 0, a sub 2 is also 0. Let's find the next non-zero term, which we expect to be x cubed. The coefficient of x cubed is negative 1 over 6. So, a sub 3 minus a sub 1 over 2 equals negative 1 over 6. Substituting a sub 1 equals 1, we get a sub 3 minus 1 over 2 equals negative 1 over 6. Solving for a sub 3, we find it is 1 over 3. The coefficient of x to the fourth is 0, so a sub 4 is 0. Let's find the coefficient of x to the fifth. The coefficient of x to the fifth is 1 over 120. So a sub 5 minus a sub 3 over 2 plus a sub 1 over 24 equals 1 over 120. Substituting the values we found for a sub 1 and a sub 3, we get a sub 5 minus 1 over 6 plus 1 over 24 equals 1 over 120. Solving for a sub 5, we find it is 2 over 15. So, the first three non-zero terms of the Maclaurin series for tangent x are x plus x cubed over 3 plus 2x to the fifth over 15. This series converges for the interval negative pi over 2 to pi over 2, which is the domain of the tangent function. We have now successfully used the method of undetermined coefficients to find the Maclaurin series for a quotient of functions. Let's recap the key Maclaurin series we've derived and their intervals of convergence. This summary is essential for solving problems efficiently. We've covered the exponential, trigonometric, and logarithmic functions, as well as the binomial series. First, e to the x. Its series is 1 plus x squared over 2 factorial, and so on. It converges for all real numbers. Next, sin x. Its series is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on. It also converges for all real numbers. Then cosine x. Its series is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on. It too converges for all real numbers. For the natural logarithm of 1 plus x, The series is x minus x squared over 2 plus x cubed over 3, and so on. This series has a finite interval of convergence, -1 less than x less than or equal to 1. Finally, the binomial series for 1 plus x to the power of p. The series involves binomial coefficients and converges for the open interval from -1 to 1. Remembering these fundamental series and their intervals of convergence will be incredibly helpful as you tackle more complex problems. You can use them as building blocks for other functions. Now, let's apply what we've learned to solve some IB-style problems. Our objective is to use Maclaurin series to evaluate limits and approximate integrals. These are common applications of Maclaurin series that you will encounter in your exams. First, let's use series to evaluate a limit. Consider the limit as x approaches 0 of the quantity e to the 2x minus 1, all divided by sine of 4x. If we substitute x equals 0, we get 0 over 0, which is an indeterminate form. We could use L'Hopital's rule, but using Maclaurin series is often more elegant. We'll replace e to the 2x and sine of 4x with their Maclaurin series. The series for e to the 2x is 1 plus 2x squared, and so on. The series for sine of 4x is 4x minus 32x cubed over 3, and so on. Now substitute these into the limit expression. The 1 and -1 in the numerator cancel out. We are left with the limit of 2x plus 2x squared, and so on, divided by 4x minus 32x cubed over 3, and so on. We can factor out an x from both the numerator and the denominator and cancel them. Now, as x approaches 0, all the terms with x in them go to 0. We are left with 2 divided by 4, which simplifies to 1 over 2. This is the value of the limit. Next, let's use series to approximate an integral. Consider the integral from 0 to 1 of cosine of x squared dx. This integral cannot be solved using standard integration techniques. However, we can approximate it using Maclaurin series. First, we need the Maclaurin series for cosine of x squared. We found this earlier by substituting x squared into the cosine series. It is 1 minus x to the 4th over 2 factorial, plus x to the 8th over 4 factorial, and so on. Now, we integrate this series term by term from 0 to 1. The integral of 1 is x. The integral of -x to the 4th over 2 is -x to the 5th over 10. The integral of x to the 8th over 4 is x to the 9th over 2 and 16, and so on. Evaluating at the limits, we get an alternating series. The value of the integral is 1 minus 1 over 10, plus 1 over 2 and 16, minus 1 over 9 360, and so on. To estimate this to 4 decimal places, we need to find the first term that is smaller than 0.005. The term 1 over 9360 is approximately 0.106, which is not small enough. The next term, 1 over 685440, is approximately 0.146, which is small enough. Therefore, we need to sum the first 4 terms. 1 minus 0.1 plus 0.0463 minus 0.00106 gives us approximately 0.9045. This is our estimate for the integral. We have now seen how Maclaurin series can be used to solve problems that are difficult or impossible with other methods, such as evaluating indeterminate limits and approximating definite integrals. Let's conclude with a final, more advanced application of Maclaurin series, proving Euler's formula. Our objective is to use the series for e to the x to derive the relationship between the exponential and trigonometric functions. This formula, e to the I theta equals cosine theta plus I sine theta, is one of the most beautiful and important results in mathematics. We start with the Maclaurin series for e to the x. The series is 1 plus x squared over 2 factorial, and so on. Now, we substitute x equals I theta into this series, where I is the imaginary unit, the square root of -1. This gives us 1 plus I theta squared over 2 factorial, plus I theta cubed over 3 factorial, and so on. Let's simplify the powers of I. Remember that I squared is -1, I cubed is -I, and I to the 4th is 1. The series becomes 1 plus I theta, minus theta squared over 2 factorial, minus I theta cubed over 3 factorial, plus theta to the 4th over 4 factorial, and so on. Now we can separate this series into its real and imaginary parts. The real part consists of all the terms without an I. The imaginary part consists of all the terms with an I, which we can factor out. Take a close look at the 2 series in the parentheses. Do they look familiar? The first series is the Maclaurin series for cosine of theta. The second series is the Maclaurin series for sine of theta. And there you have it. By substituting into the Maclaurin series for e to the x, we have proven Euler's formula. E to the I theta equals cosine theta plus I sine theta. This is a beautiful example of how Maclaurin series connect different areas of mathematics and provide a rigorous foundation for complex numbers and trigonometry. We have now covered the core concepts of Maclaurin series. Let's quickly review what we've learned. We started with the definition of a Maclaurin series as an infinite polynomial approximation centered at x equals 0. We learned how to derive these series by finding derivatives and evaluating them at 0. We also saw that we can use a finite number of terms to create a Maclaurin polynomial, which is a useful approximation. We discussed the critical concept of convergence, understanding that a series is only a valid representation of a function within its interval of convergence. Finally, we explored powerful techniques for manipulating series: substitution for composite functions, term-by-term addition and subtraction, and term-by-term differentiation and integration. We also saw how to multiply and divide series to find the first few terms of a product or quotient. Maclaurin series are a fundamental tool in higher-level mathematics, with applications in physics, engineering, and computer science. Mastering these concepts will be invaluable for your future studies. To solidify your understanding, here are 5 practice questions in the style of the IBAA-HL exam. Pause the video and try to solve them on your own before watching the solutions. Question 1 asks you to find the Maclaurin series for a function and its interval of convergence. Question 2 involves using a known series to find a new one. Question 3 is a limit problem. Question 4 is an integral approximation. And question 5 is a division problem. Take your time, show your working, and remember the techniques we've discussed. Good luck. Welcome back. Let's go through the solutions to the practice questions. Here's the solution to question 1. We can use the known geometric series for 1 over 1 minus x and substitute negative 2x for x. This gives us the series 1 minus 2x plus 4x squared, and so on. The interval of convergence is found by ensuring the substitution, negative 2x, is within the original interval, which gives us the absolute value of x is less than 1 over 2. For question 2, we substitute negative x squared into the Maclaurin series for e to the x. This gives us 1 minus x squared plus x to the 4th over 2 minus x to the 6th over 6. These are the first 4 non-zero terms. In question 3, we substitute the series for cosine of 3x into the limit. The ones cancel, and we can factor out an x squared from the numerator and denominator. As x approaches 0, the limit is negative 9 over 2. For question 4, we first find the series for sine of x squared by substituting x squared into the sine series. Then we integrate term by term from 0 to 0.5. We need to sum enough terms so that the next term is smaller than 0.005. The third term, 1 over 120 times 0.5 to the 5th, is approximately 0.026, which is small enough. Summing the first 2 terms gives us an estimate of 0.041. Finally, for question 5, we use the method of undetermined coefficients. We assume SECx is a series of sub 0 plus a sub 1x, and so on. We multiply this by the cosine series and equate coefficients with 1. This gives us a sub 0 equals 1, a sub 1 equals 0, and a sub 2 equals 1 over 2. The first 3 non-zero terms are 1 plus x squared over 2. I hope these solutions have helped clarify the concepts. Keep practicing, and you'll become proficient in working with Maclaurin series. That concludes our video on Maclaurin series. We have covered the definition, derivation, convergence, and various operations on these powerful series. You should now be able to derive Maclaurin series for functions, understand their intervals of convergence, and apply them to solve problems involving limits and integral approximations. Remember the key series and techniques we discussed. With practice, you'll find Maclaurin series to be an indispensable tool in your mathematical toolkit. Thank you for watching.